Okay, this is the final part of this Edexcel Unit 4 paper in physics from October 24. A lot of you waiting for it. I've done several parts already. I can't remember if this is part 6 maybe. So I've done the longer questions in individual videos and the earlier questions in combined. So multiple choice was part 1, questions 11 to 13 was part 2, questions 14 and 15 were part 3, and then I think that as the questions got longer, I spent more time on them, so I made them into longer videos. Alright, so the only question left to go through is question 18. So don't forget to like, share and subscribe. I'm not getting as many likes as I'm getting views. If you're watching it, it means you must be using it. And if you're using it, you must be finding it useful. And if you're finding it useful, then I think just showing your appreciation by hitting that like button every time you watch one of my videos, that is all the payment I need. The service is free to you as users. I don't get paid for this. This is done in my free time. So a little bit of gratitude would be appreciated. Thank you very much. My number one country that I get the most people watching from seems to be Bangladesh. So thank you to Bangladesh and all the viewers I've had last year and this year. This is a new channel. This is just entering its 2nd year. So hopefully we'll get 1,000 subscribers or more very soon. We're getting about 3 or 4 new subscribers a day during exam season. So do share the videos with your friends if you think they'll appreciate it. Okay, and give me a comment about why you follow my channel and any other channels that you find useful. So just so I get some feedback from you as well. Thanks for watching. Okay, so question 18 is the final question in this paper. Yeah, and remember the final questions are normally longer. Okay, and this is another 17 marker, and it's on tracks in a bubble chamber. So the diagram shows a track of a pi plus particle, not a pi, is that epsilon? Yes. Sigma? Yes. Or I think, I don't remember what letter that is. Anyway, whatever this letter is, particle in a bubble chamber. So in a bubble chamber, the charged particles can produce tracks because they create ionization, and that creates the ionization, creates the bubbles that allows you to see the pattern of the tracks. Okay, the particle decays, it says, at the end of its movement at point X. So we're going to work out what happens at point X. So that means we know that the particle is moving this way with speed, and we know that the magnetic field is causing it to curve towards the right. So the force is at right angles to the velocity. Now it says there is a magnetic field of flux density B, yeah, perpendicular to the velocity of the particle. And that's what's causing the sideways force on the charged particle. It's positively charged. This particle, whatever it's called, is following a circular path, and the radius of curvature is 1.99 meters. Okay? Now remember, you have this equation given to you on your equation sheet. Okay? So you've got to use this equation. Just going to draw it again because it was hiding the R. So this equation is given to you. Now, since we know R and we want to find out B, we've been given the momentum of the particle here. And remember, momentum is P in this equation, which is mass times velocity. So we know P, we know R, we know Q, because Q is +1. So it's 1.6 times 10 to the minus 19. So once you know all that, all you've got to do is change the equation round to make B the subject of the equation, put the numbers in. Once you put the numbers in, there you go. You get 1 mark for using the equation. Make sure you don't make any mistakes. I think you don't need to do any, everything's been given in SI units. So when you do that to 3 significant figures, it comes out to 1.15 Teslas, and most of the data is provided to 3 significant figures, including Q, which I think is 1.60 in the data sheet. Okay? So really, I should have written the answer in this space, but I don't think they'll penalize you. So it says the equation shows the decay of the particle. So the decay is that. There's your balanced equation. I want to check that it's balanced. This particle is made of 2 quarks and 1 strange quark. 2 up quarks and 1 strange quark. Now baryons are made of 3 quarks. So this particle must be a baryon. Yeah? So 1 mark for recognizing that it's a baryon. Now it says deduce whether the conservation of charge, so we're doing the conservation of charge and the conservation of lepton number. Do they apply to this decay? So I've rewritten the equation out, yeah, and underneath it I first analyzed charge. Okay, well, the original particle has a charge of +1, as you can see. Pi plus is a +1, and a neutron is neutral. So you've got +1 on the left-hand side here, +1 on the right-hand side for the pion, the pi plus meson, and a neutral charged particle. So the charge on the left-hand side is equal to the charge on the right-hand side, and you've got to show that clearly, that you know that charge is conserved because the charge on the left-hand side is equal to the charge on the right-hand side. So the only thing I could be making sure that the examiner understands it is by saying writing what I just said, okay? But I think my method is clear enough. And then I'm analyzing the lepton numbers, yes? And since the original particle is an up strange particle, you know it's not a lepton, so its lepton number is 0, okay? And a meson is a charge and is a quark anti-quark combination, which is not a lepton because it's made of quarks. Anything made of quarks is not a lepton, and a neutron therefore is also not a lepton. So there are no leptons involved. So lepton number must be conserved, because you see you had 0 leptons to start with and 0 leptons to finish with. A very easy 4 marks, as long as your working is shown as clearly as mine. The next part is about conservation of momentum. So we've done conservation of charge, conservation of lepton number. They could have told us to do conservation of baryon number as well, but now they're telling you to analyze the momentum. So the diagram shows the directions of the 3 particles involved in a decay. So initially, all the momentum is in the original particle, and then it splits, yeah, so it's moving vertically upwards, and then it splits into the pion to the right and the neutron to the left, okay? They've given the angle for the pion to the vertical, and they've given the unknown angle of the neutron to the vertical, and they're stressing that this is not to scale, so you can't do any measurements on it, yeah? You've got to do calculations. They want you to determine the magnitude and direction of the momentum for the neutron. So they've given you information for the original momentum of the original particle, and they've given you the momentum for the pion, yeah, after it splits into the 2 particles. So we've been given some information. Now, what do you do? How do you solve this problem? So first of all, if you look at the x component, yeah, in the x left and right component, the neutron momentum will be one way, say negative, and the pion, meson, the pi meson, will be to the right. So if we count the right as positive and the left as negative together, they should add up to 0, yeah, based on the conservation of momentum, okay? So this is also the momentum conservation, yeah? So as long as you show that you know conservation of momentum, that in itself is worth 1 mark, okay? Now you'd have to do that twice in the x component and the y component. So you could say that the neutron momentum is the negative of the pion, the pi plus meson momentum. Now remember that if we're talking about the x component, we want the x component of the pion, yes, in this direction. Let's draw that again. I'm going to change the color as well. So the pion has an x component. So this is the component of that line in the x component, so it'll be sine 65. Yes? So that's why it's a sine 65 there, because you're going away from the angle provided. Yes? So once you got the sine 65, they've given the momentum of the pion after it's created. Yeah? So it's the sine 65 component of that momentum. And once you do that, you can find out that the momentum is 9.7 times 10 to the minus 20 kilograms meters per second. So if it's to the right, it will be positive, and I'm saying to the left is negative. So that will be the magnitude of the momentum of the neutron in the x component. So you can also then do the same by looking at the y component. And in the y component, all the momentum initially was in the original particle before it decayed. It then, some of the momentum of that turns up in the neutron and some in the pi plus meson. And together they must equal the momentum initially. Initially we know the momentum, it's given in the question above, 3.67 times 10 to the minus 19. We don't know anything about the neutron's momentum, but we know that the pi plus meson has a total momentum of 1.07 times 10 to the minus 19. And this time you want the component upwards. Let's do that in red. So it'll be upward component of this arrow. Let's do that in red again. See if I can get... So it's that part of the triangle upwards, okay? So that's the component upwards, and that's going to be, this time, it's going to be this cos of 65 in the x direction. So you're basically doing the same as before, resolving in the vertical component will be cos 65, whereas resolving in the x component will be sine 65 of the same momentum, 1.07 times 10 to the minus 19, okay? So we've now got at least 2 or 3 marks, I would say. So you can then work out the unknown, which is the momentum of, in the y component of the neutron, yes? So it will be, you change the subject of the equation, you take away the momentum of the pion from the original momentum of the originating particle, and you'll get the y component of the neutron, up being positive, as 3.22 times 10 to the minus 19. So you've now worked out 2 components of the neutron, and all you've got to do to work out the total momentum is use Pythagoras. Yes? So once you use Pythagoras, yeah, it's the y component squared plus the x component squared, yeah, and then square root it. So you put basically the 2 values we just talked about under the square root sign, and that's using Pythagoras, and you'll get the total neutron's momentum as 3.36 times 10 to the minus 19 kilograms meters per second, and that's its magnitude. So then, how do you then work out its direction? Yeah, its direction is then given by this triangle, analyzing just the two components of that theta right angle triangle, but remember it's not to scale, so you know the upward direction is the y component of the neutron that we just calculated, yeah, and the x component is to the left. So those two you can do opposite, yeah, over adjacent, and that will give you the angle, okay? So you can, those values are shown here. Opposite was the y component, so the y component is this value, and the x component to the left, which is negative, is this component. You divide that, and that will be tan of the theta that we want to work out. Yes, so that's the last part of the question. You get the ratio as 0.301, which gives you an angle of 16.8 degrees, and all that's left is for you to write them in the spaces provided here. Okay? And I think 3 significant figures is accurate. So you've got the magnitude is there, and the direction is there. Hope that makes sense. The final part of the question is 4 marks, and I think it's a very generous 4 marks. The diagram shows the track of the sigma plus particle, yeah? So initially, this is the direction which we looked at the beginning, and then at x it decays, and you'll notice that I haven't drawn the neutron in there because the neutron has no track since it's an uncharged particle and therefore does not ionize and create bubbles in the bubble chamber. Okay? So uncharged means no tracks in the bubble chamber. All right, so you only want the pi plus particle to show a track, and we know that it was moving to the right. So you want to show that it's moving to the right, and you want to show that its curvature is greater than the curvature of the original particle. And why is that? Because it has less momentum. And if you remember the equation, R equals P over BQ, R equals momentum over BQ, both of these particles have the same charge, both are in the same magnetic field, so the radius of curvature is proportional to the momentum, yeah? So the R, it will be, have I got it right? Let me just check if I have it right. So you've got to find this on your formula sheet. So let's have a look on the formula sheet at the equation I am suggesting. So here's the formula sheet provided at the back of the exam. And right near the end, yes, you have, in fact, this formula sheet. So in a magnetic field, the one with the bigger momentum will have the bigger curvature. Yeah? The bigger the momentum, the bigger the R. Doesn't seem to make sense. Okay? So I'm confused myself on this. But that's the mark. It's got to curve more because it has less momentum. Oh yes, it has less momentum. So I'm just confusing myself. It's the momentum of this particle. The momentum of this particle is less so its radius is smaller, so its curvature will be larger. I'm sorry about my own mental confusion. I've been spending too much time on this physics paper. Okay, so I hope you found that final question useful. Apologies for the confusion, but you can see how easy it is to lose marks when you're tired. Okay, once again, thank you very much for supporting my channel, and please help to get more students to watch it by sharing it with your friends and making go to the top of the charts in the algorithm for the YouTube by liking every single video you watch. Smash that like button. Thanks again, and more videos on the way once I get some more free time. I don't know what will be next. I might try to do the Unit 1 for mechanics, because that exam is on next week too for students doing Unit 1. Okay, thanks for watching. Bye for now.